Innomotics is back on stage again, and we have another real expert here on stage when it comes to turbine replacement. He knows everything about it. Please welcome Gijs Van Maanen. Hi, Gijs. So you are our expert in turbine replacement. I think you have more than 30 years experience in the oil and gas business, which is quite a lot, with this focus on our high-speed motors. And I don't lie if I say your mission is emission reduction, right?
Exactly. So energy transition is ongoing, is happening now. And we are supporting industry to achieve their emission reduction targets required for a sustainable future.
Okay, and now let's turn to the turbine replacement. Why do we do that? Why do we push this replacement at Innomotics?
Well, that's a good question. Let's start right from the beginning. So, looking at this graph shows that in the global emission, we are sending 40 gigatons of CO2 into the atmosphere. So we all went to the Paris Agreement, aligned with the Paris Agreement from 2015, and we have to reduce to keep the temperature rise within 1.5 degrees on a global scale. So if we are doing nothing, just proceeding as we do now, or we follow the red line like you see here, right? So it's getting worse and worse and worse with disastrous results for mankind. So factually, the blue area represents the requirements to keep the temperature rise within 1.5 degrees. At the moment, as we are speaking now, we are just somewhere in the middle. So we are not following this blue line. And that is where we have to change. So we and you as operators of the steam turbines have to change. So just starting your journey. According to an old saying, a turbine a day keeps the heat away. So join us and learn about the next topics. So here you see a typical turbine replacement arrangement. So you see that on the steam turbine, you need a lot of steam, and this steam is generated in a boiler or in something else. But you need for that the fossil fuels, and there actually the emissions are coming from. The steam is generated, and then you have an HP, high pressure steam stream, medium pressure steam stream, and then it's connecting to the steam turbines. If you're taking away such kind of steam turbine, is disturbing your steam balance of plant. This complete overview is getting disturbed, and you need to redo. This is a quite complex task, and we are supporting you in that. On the other hand, you see the electrical drive. The electric drive is not fueled by fossil fuels, but by electricity. Of course, removing the steam turbine, replacing an electric motor is fine, but you need also an electric drive to drive this motor, transformer, and of course a connection to the grid. And there, of course, we have the key topic. If you're connecting to the grid, with pure green electricity, you have nice savings. But here in Europe, generally, we still have an emission rate of 25 to 35%, right? So that means you have an electricity, a green content in your electricity, but this will reduce significantly and rapidly in the near future. Talking about an example. Here we replaced an 11 megawatt steam turbines. Actually, there were several steam turbines at a certain customer location. And here we saved over 116,000 tons of CO2 emissions a year. So in average, between 110 and 120. Of course, this is assuming green electricity if it was in Norway, for example, where the power generation is based on green electricity, you have this full emission savings. If you have grey electricity or a mixture, then of course it's less. So now talking about efficiency increase. You saw this boiler system which is responsible for the steam generation on the beginning. This boiler system has a very poor efficiency rate, resulting in an overall efficiency of the steam turbine between 24 and 34%. On the right-hand side, you see the electrified drivetrain. And the electrified drivetrain contains of the equipment that you are replacing on site, but you have to count, of course, the efficiency rate of the power generation remotely, off-site. And this results in an overall efficiency between 45 and 54%. But main message here with all of this, there are three main things. You are reducing carbon emissions by 94%. You are reducing your emission tax numbers in the operational cost, and you are doubling your efficiency, which is not only a nice to have thing, but it's also really an economical benefit in your process. To finalize this topic, just have a look at this figure. If you look for a gas turbine, for example, there are two main contributors to your operational cost, being emission costs and being fuel costs. And of course, a little bit else, coming to later on that. When you look to the electrical drive system, however, you are seeing that the cost contributors for the emissions are really low, and the majority is fuel cost, electricity, that you have either to buy from the grid or generate yourself. The third factor that is obvious here is the maintenance cost. Operating a gas turbine or a steam turbine provides significant maintenance required either on the gas turbine itself or on your steam generation system. If you're putting in an electrical drive, this is running for 6 to 7 years uninterruptedly, right? So that means no maintenance in the meantime. And if you have a shutdown, somewhere a turnaround of your refinery in one of the 6 or 7 years, you only need to replace some consumables like fans, batteries, and things like that. So that means the operational cost and the maintenance portion is very, very low compared to your steam and gas turbines.
Yeah, this is quite a lot of savings which you are explaining here. So to sum it up, that means emissions can potentially go down to zero, which is really awesome. And on the other hand, it's also commercially very attractive to replace these old turbines. So, but I can imagine it's not so easy to replace. It's not just plug and play, yeah? So can you maybe tell us more about the challenges that customers are facing within these projects?
Yeah, that is perfect. That's a good question. So, to be honest, talking about steam turbine replacements is quite easy, right? But getting it practiced is a difficult job. But there are challenges, like you see here. So, still talking about steam turbines is typically regarding replacing a high power density piece of equipment into an electric motor. And that, especially for the lower power, below 8 megawatts, this is significantly challenged because the dimensions of your steam turbine is really limited. So when you are going to replace this with an electric motor, this has to fit on the tabletop foundation, and this is really a challenge. But of course, if you choose the right products, you can cover these challenges. The second thing, of course, is your structural dynamics of your tabletop, because this is a tabletop. It is actually 4 concrete pillars and some frame, which is 30 years aged, usually. So, and then putting an electric drive on there with other rotordynamic behavior is could be a real topic. So you have to think to think these topics in advance and then act accordingly and select the right equipment. So here you see one of the options with our high-speed motors, replacing these steam turbines. So this is are the frame sizes we have available, and you see now that if you take, for example, you need to replace a steam turbine of 10 megawatts, 7,000 RPM, just as an example, then if you focus on this, you can see that you have 3 different options to apply motors. So that means we utilize and design our motor exactly according to the needs of this plant and of the dimensions to meet the dimensions of your steam turbine that you're going to replace. So on the other hand, the right-hand side, you see the drive technology. Of course, we talked, it is not only about motors, it's also about drives. So for this steam turbines replacements, we typically provide our cell-based drives with clear benefits, which I talk later a little bit about. And that means we fit our drive technology exactly to the motor. And then we can add redundancy measures to meet your mean time between failure requirements on site. And meet to this 7 years operation, 5 to 7 years operation requirement. So focusing on the footprint and the tabletop. Of course, many times I get the question, yeah, but we want to replace with a conventional speed motor, 1,500 RPM. Also, this is possible, and of course, we're supporting that, and we have the equipment for that. However, especially for steam turbine replacements on this big tabletop, there are challenges. And few of these challenges you see here on this picture, right? The first is, of course, the dimensions, what I've already said. If you add a 1,500 motor to this compressor, you need a speed change. You need a gearbox in between. So you shift the motor in axial direction, and then it's looking over the foundation. But more important, you not only have an axial displacement due to the length of the drivetrain, but you have also a radial displacement that the motor is getting displaced, and this big weight of this motor is just sitting at the edge of the foundation or even looking over the edge. So, and that is, from structural dynamic point of view, this is a real challenge. And that is the reason that for this kind of projects, we always propose these high-speed motors. So, the next thing, a little bit focusing on drive technology, which is very, very important. Here you see what is the result of applying the multi-cell technology. Multi-cell technology means you have many cells building the voltage, the output voltage, and that means that you see here the output voltage going to the motor, which is more or less a perfect sinus, which is not quite obvious for all kinds of drives. If you have a 3-level drive or a 5-level drive, that's usually done with many of our competition, you see this is real harmonics in the sinus, and this is resulting into output torque pulsations. And the output torque pulsations is a real risk for your existing coupling and your existing coupling hub on your compressor shaft. And to safeguard this, we apply multi-cell technology with this perfect sinusoidal voltage, and then the topic is saved. So finally, only focusing on motors is the high-speed motor technology. Here you see the high-speed motor technology with up to 16,000 RPM, resulting in extreme high forces, up to 40 kilonewton meters, a surface speed of almost speed of sound, and a maximum eccentricity required below 10 micrometers in order to keep this drive running for lifetime. So with this technology, we have more than 6 million cumulative operating hours in our references, and by that, it's proven technology. Last thing, talking about turbine replacement projects, very important, don't forget the time. Think 3 years ahead. Why? Because your turnaround schedule in the refinery is a fixed date. You are not flexible. If you do not meet that date, there is no project. So be prepared and start early. Think 3 years ahead.
Okay, our customers should be the early birds, yeah, and start, in best case, today with their projects. Good, Gijs. I'm sure you can show us already some references where we successfully replaced turbines.
Yeah, exactly. That's of course good. Always having references is good. We can show to customers, and of course we are very proud of this. So one of these references is, we did it a long time ago, is the most smallest motor we ever had. This is below 1 megawatt replacement. You see on the turbine size, you couldn't imagine that you can replace this with an electric motor. However, on the right-hand side, you see we removed the turbine, placed the high-speed motor, and this is now running for more than 8 years exactly. The second reference is a nice example project. It's an 8 megawatt project running in Spain with customer Repsol. It's a high speed to saving 25% of emissions. This example, for example, is a fully digitalized drivetrain, which is also possible, monitoring everything. And we are able to support the customer to even improve their operational costs and long-term running for a 7 years operation.
Yeah, thank you.
In addition, this is not showing here, we are doing many other projects, but I cannot show them. If you want to know more, come to me at the booth, and then we can have close discussions. 2 things I want to say to you. We are running now, doing replacement projects for big power, 25 megawatts, saving 200 kilotons a year only by replacing 1 turbine. The second thing is we are replacing turbines offshore on a grid, electrifying a platform, not only with turbine replacement, but also with total electrification with VFD technology. Here we are replacing 2 turbines, saving 250 kilotons a year, extended by, again, 2 turbines, so 4 turbines in total, saving up to 500 kilotons a year, being almost 1% of the Norway emission in total. And that is why we are doing this, and that is where I get the spirit from.
Very, very exciting examples. I'm sure you have more references. How many did you do in average?
Well, steam turbine replacements, we do it already for a long term. We started with gas turbines, now we are steam turbines. Basically, we have more than 50 references running around.
50. So you seem to be very experienced and passionate as well. So then let's invite the visitors to our booth. Maybe you go to the next slide, which is our call to action, I would say.
Yeah, so finally, closing the topic, the energy transition is ongoing. Emission targets are tightened and tightened, but with the right equipment and the right partners, you can manage the challenges of these projects. With that said, come to us, come to Innomotics, and we find the right solution for your turbine replacement project.
Bye-bye turbines, and hello to our visitors and customers to come to us. Thanks a lot, Gijs, for this exciting presentation. Thank you.